Linear programming is the method used to find an optimal value of a function subject to constraints. And in the real world, things are subjected to constraints, like we saw in the last section. It's the amount of hours we have available of workers. It's the amount of land we have. It's the amount of resources we have. Put constraints on how much we can produce. And most of the time we want to minimize costs and maximize profits. So that's what we're really doing in linear programming. So this is a very important topic. So we're going to be using our graphical method, drawing in those inequalities of our constraints. And those inequalities give us a region. Any point in that region may yield an optimal value for the objective function. So any point in there is a feasible solution. The region is called the feasible region. So we're going to try to use that region to narrow down the possible solutions to find the best solution. So when the feasible region for a linear programming problem is closed and bounded, so like when we had those that were around the x and y axis like this, our objective function will have a maximum value and a minimum value. If it's not closed or bounded, we might still have a maximum, we might have a minimum, and we may not be able to solve it. But those maximum and minimum values are actually going to occur at a corner of the feasible region. Now sometimes two corners work, so then we'd have optimal values at any point on the line connecting those two corners. That doesn't happen as often, so let's just see where we go. The first part of it is, though, we have to be able to graph what we have and look for those feasible values. I find that using the intercept method to graph really does help here. So instead of solving for y and using the calculator, I'm going to use the x and y intercepts. Now this is our bounded region. These are constraints. This up here is what is called the objective function. It's what we're trying to find the solution of, and we're trying to maximize it. So we're trying to be able to plug in an x and a y and get the biggest f we can. So let's find our x and y intercepts. So on the first one, if I plug in 0 for y, I get 50 for x. And then if I plug in 0 for x, I get 10 for y. On this one, my x-intercept will be 14. My y-intercept to be 28. And then we have the conditions of that x is greater than 0 and y is greater than 0. So that means we are definitely in the first quadrant. And I need to go all the way to 50. So let's count by tens. 10, 20, 30, 40, 50. 10, 20, 30, 40, 50. Now the first line has an x-intercept of 50 and a y-intercept of 10. So here it goes. And it says we're less than that line, so it'll be underneath. X-intercept at 14, so about here. And y-intercept at 28, about there. So I'm talking about this region here. Now this point was the x-intercept that I just drew in, and that's this line right here. So that's the point 14, 0. This corner is the y-intercept from the first one, so that's 0, 10. I know this is 0, 0. And I need to find this other point here. So I need to solve this system of equations. And you've learned lots of ways to solve systems. You could solve for y and put them in the calculator. You could use matrices. I think I'm going to do it algebraically, just because I'm crazy like that. So I'm going to multiply the first one by a -2 and get -2x minus 10y equals -100. When I add them together, I get -9y equals, that would be a 72, a -72, sorry. And then if I divide by 9, I get y equals 8. If I plug that back in, let's say to that second one, 2x plus 8 equals 28. 2x equals 20. X equals 10. Whoops, 10 comma 8. So I have 4 corners of my graph. And any of these could be the minimum or the maximum. And we just need to test all the values. So we're testing them in this function, 3x plus y. And I like to make a little table. So I have my point 0, 0, 0, 10, 10, 8, and 14, 0. If I plug it in the first one, so 0 and 0, I get that f is 0. So I've kind of made a little table here. If I plug in 0 for x and 10 for y, f is 10. Let's see. 10 for x, that makes it a 30, plus y, that's 38. And then 14 times 3, I'm not good at that. 14 times 3 is 42. So f is my largest value, and we were trying to maximize, f equals 42 is my largest value. So f is maximized at 14, 0. I really think this is going to make much more sense when we put the real life situation in it. So the next example we're going to do actually should look familiar, because we've kind of done it already before. It's about the farm co-op that had 6,000 acres. And so we had the equations. Let me see if I can pull up my copy, because we had that the acres had to be 6,000. So we had corn was X and soybeans were Y. So we had the equations X plus Y had to be less than or equal to 6,000. Then the fertilizer, that was 9x plus 3y, had to be less than or equal to 40,500. And then the labor was 3/4 times x plus 1 times y, had to be less than or equal to 5,250. And again, our x had to be positive and our y has to be positive. So we ended up, and I am looking back at our notes here, with this beautiful region. So we already had our corners of the region. Let me write them. Well, first off, let's. I don't want to get ahead of myself too much. We need to talk about what we're trying to find here. If the co-op's profit per acre are $240 for corn and $160 for soybeans, how many acres of each will maximize profit? So my profit equation would be 240 for corn plus 160 for soybeans. And we're trying to figure out what will maximize that profit. So let's talk about our corners and the profit at each corner. So I'm going to pull back up my graph, and we need to actually write down all the corners. Even 0, 0, which that's going to give me a profit of 0. So that's my minimum. I also have the point 0, 5,250. I have the point 3,000, 3,000. I have the point 3750, 2250, and 4,500, 0. And we're going to test each of those in that equation. So I'm going to just do 240 times, well, that's 240 times 0. That's not even worth it. So 160 times 5,250. So that's if we only planted soybeans. We'd make $840,000. What if we do 3,000 of each? So 240 times 3,000 plus 160 times 3,000. Ooh, that's better. That's 1,200,000. 240 times 3,750 plus 160 times 2,250. Ooh. $240 times 4,500. So this is if we plant only corn. You get $1,080,000. So on part A, we should plant 3,750 acres of corn and 2,250 acres of soybeans for a maximum profit of $1,260,000. That's a nice profit. Now, part B says if market conditions change so that the co-op's profits per acre change to $300 for corn and $100 for soybeans, how should the co-op adjust its planting to maximize profit? So in other words, we're trying to see if that changes anything. So we would make a new table, and we have a new profit equation. I'll just do like a P with a star. Okay. It says it's going to be $300 for corn and $100 for soybeans. Again, we're going to make the same table. We're using the same corners. None of that has changed. Our constraints are the same. And I'm literally just plugging each of those in. So 100 times 5, oh, I could have known this one. That's just 525,000. $1,200,000. Ooh. So our maximum profit actually occurs at either the point 4,500 or the point 3,750 to 250. This means that the profit function P will be maximized not only at those two corner points, but any point along the line connecting them. So, any point along this line. So it actually have to be any point between those 2 points. So any point along the line, and I have to figure out which line that is. That was the red line. Red line was this one, 9x plus 3y. And if we're talking about the line, it's just an equal sign. 9x plus 3y equals 40,500. Will give us a maximum profit of $1,350,000. Find the maximum and minimum values of C equals X plus Y. So again, we want to draw our constraints. I highly recommend using y-intercepts where we can, intercepts. So I'm going to do my x-intercepts and y-intercepts. I'm going to make the first line be my red line. So I'm going to decorate this one in red. So the x-intercept is going to be 6. The y-intercept is going to be 4. I'll make the next one green. X-intercept is going to be 2. Ooh, the y-intercept's actually at a -4. Okay, so we have to take that into consideration when I'm drawing the graph, but that's okay. And then we have the constraints, so we're really only looking at positive x and y values. So, okay. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4. So the first line is connecting this x-intercept and this y-intercept. And we're shading below it because it says less than. Now with this negative one, I want to kind of maybe even rewrite that. Let's solve for y. because I want to talk about where I'm going to shade on that one. It flips the sign when I solve for y. So this one we're actually shading above the line, even though it said less than. It's because we had two different signs there. I'll show you another way I could find that too here in a second. I could have also plugged 0, 0 in, and 0 minus 0 would be less than 8, so we are talking about above this line. We're talking about below the red line. But we've got to be in between. Keep all our x's and y's positive. So we're talking about this region here. So I need to have all my corners listed out. And then we're going to be plugging them into the objective function. So 0, 0 is one of the corners. This corner's at 2, 0. This one's at 0, 4. And how do I find where these two are meeting? It looks like it's at 3, 2, but I can't guarantee that. So I would have to come off to the side, maybe, and solve that system. So I have 2x plus 3y equals 12. 4x minus 2y equals 8. If I take the first one and multiply by a negative 2, I get negative 4x minus 6y equals negative 24. That's going to be negative 8y equals negative 16. Y is 2. 4x minus 2 times 2 equals 8. 4x equals, that's a 4, so that would be 12. X equals 3. So it is the 0.32. I just wanted to double check it. And we're going to plug this in, and this time we're labeling which ones are the minimums and the maximums. So if I plug in 0, 0, I get 0. Two, 0, I get 2. Excuse me. I get 4, and I get a 5. So this would be the max, and this would be the min. And that's going to come into play in the next one when we're finding a minimum. So minimization. All right. And I did not give myself a lot of room on this one, so I may be grabbing some scratch paper here in a little bit. 2 chemical plants, one at Macon and one at Jonesboro, produce 3 types of fertilizer. Low phosphorus, medium phosphorus, and high phosphorus. At each plant, the fertilizer is produced in a single production run, so the 3 types are produced in fixed proportions. Okay, so we've got low phosphorus, medium phosphorus, and high phosphorus. We're making them at the Macon plant and the Jonesboro. Okay, so I always like to make a table. The Macon plant produces 1 ton of LP, 2 tons, and 3 tons in a single operation, and charges $600 for what is produced in one operation. So $600 in Macon. Jonesboro does 1 ton, 5 tons of medium, and 1 ton of high, and it charges $1,000 for what it produces. If a customer needs, okay, so we got a need. We need 100 tons, 260 tons, and 180 tons of HP. How many production runs should be ordered from each plant to minimize the cost? And remember, these are the costs to run it. Okay, so first off, I want to talk about what that needs means. If the customer needs 100 tons, is it okay to make 105? Yes. Is it okay to make 90? No. So we need to be greater than that. So since we're trying to figure out how many production runs are coming from each plant, let's let X be the number of runs at Macon and Y be the ones at Jonesboro. So my cost is going to be Macon at $600 for each run, and Jonesboro it's $1,000 for each run. So this is what I'm trying to minimize this time. Now let's look at our inequalities. 1 ton plus 1 ton, we need at least 100. So this is X plus Y has to be greater than or equal to 100. 2X plus 5Y has to be greater than or equal to 260. 3X plus 1Y has to be greater than or equal to 180. And we couldn't run negative amounts. So I'm going to grab a scratch piece of paper real fast. And actually I found grid paper. Oh. Okay. So let me do my intercepts. The first one's going to have x-intercept at 100 and y-intercept at 100. The next line, x-intercept's going to be at 130, and the y-intercept is going to be at 260 divided by 5 at 52. Another line, another color. X-intercept would be at 60 and y-intercept at 180. Whoops. We don't have to be perfect on this. What if I count my 20s? 20, 40, 60, 80, 100. 20, 40, 60, 80, 200. 20, 40, 60, 80, 100. 20, 40, 60, 80, 200. The first line is connecting 100 and 100. And if I plugged in the value 0, 0, 0 is not in this solution. I've got to do more than that. So I know I'm going to be above this line. The next line is going to be x-intercept of 130. So it'll be right in between. And y-intercept of 52, 20, 40, 50, somewhere in there. And again, if I'm having to make more, then I need to be above that line too. The last one, the x is at 60 and the y is at 180. That's up here. So we're going to have to find some crossings because we need to be above all of those lines. In other words, I need to be out here. This meets all the conditions. So this point is at 0, 180. This point down here, that was at what, 130? Right here? That's at 130, 0. Now I need to find these 2 points of intersections. So the first one I'm going to find, I'm going to do the red and the green line together. X plus y and 2x plus 5y equals 260. This is going to be the red line and the purple line. The red line was this one, and the purple line was this one. So I need to solve those systems. Again, you've learned many ways to solve. I'm using the elimination method because it's the fastest to me. So we have 4 corners, and we want to know our cost at each of those 4 corners. And I'm just copying these straight over from that scratch paper. We're going to be plugging each of these into the cost function. For the first one, it's nothing happening at plant X, which was Macon. Everything's only being done in Jonesboro. So it's 1,000 times that 180. That's $180,000 cost. $600 for 80 units and $1,000 for 20 units. Leaves me with $68,000. And then let's see, 600 times 40 plus 1,000 times 60 gives me 84,000, and then 600 times 130 is 78,000. So the best option seems to be if we do 80 runs at Macon and 20 runs at Jonesboro, minimize the cost.